right to it. I'm going to go ahead and show everybody my screen really quickly, and I'm just going to kind of get everyone caught up in just a minute or two, just so everybody knows what book we're reading, where we're at, and where we are with the code. So basically, the name of the book was in the event description. So if you go to Meetup or you go to the top here in our events, you can see Machine Learning Mastery Club, and the name of the book is here. Right now, we are working through chapter 2. In the event description, I said just try to get caught up and read chapter 1. If you read chapter 1, you're going to understand at least enough of the fundamental concepts of machine learning where you could kind of conversate and talk about what we're doing here. We're working through an end-to-end machine learning project, so we're about 1/3 done, and we got about 1/3 done in the last 2 weeks. And next we'll be moving on to classification, decision trees, neural networks, all the other fun stuff. But this is a really, really cool project that we're building here as well. So I'm not going to go over the rest of the chapter, but I will show you the code that we have so far, since I am reading through the chapter just line by line, and we're typing the code as we go through it. If there's any concepts that we don't understand, then I'll have someone go and do a detour, a quick little Google search, and then come back and let us know what they found. Or if there's something that you don't understand as we're working through the book, feel free to just do your own detour without me having to tell you, and just come back and share what you've learned, either by unmuting and just saying, hey, I have a little bit of information about this concept, or just post it in the chat here on the right. So if you look, we're in the machine learning. Feel free to click on this open chat here and type right there if you're just still doing research or don't want to interrupt whoever's talking. So far, we have imported a couple different libraries. The first thing we did was we created a function where we're actually loading the housing data. So we are pulling the data from this URL right here, and we are storing it in our data sets. Then we print some of the data just with a couple different methods on the data, and then we show what it looks like with the histogram. This here commented.
Will that fit in the chat? Could you copy paste just where you're at? There's a code behind it. I can just paste it in my code.
Yeah, let me go ahead and actually I could. Show, and then yeah, should be able to get the rest here. All right, perfect. Oh. Chat.
Awesome. That works.
Cool. That's that right there. So this thing that I have commented out is the first strategy that we used for separating our data into a training set and a test set. The reason why we're not using that method is because, let's just say you split your data into a training set and a test set, and you have like 80% of your data is a training set and 20% of your data is a test set. And then you do it again, and then you do it again, and you do it again, and you do it again. Eventually, the more times you do that, the more likely it is that the test set from the beginning becomes the training set eventually, because you're just shuffling it randomly. So it all just mix and matches, and it makes your model perform poorly. The second method we had here was just
Jim, are you sharing a screen?
oh, sorry. Yeah, I clicked out for a minute by accident, and then okay, cool. So yeah, the uncommented, that's the one that you don't really want to use this strategy, but the book showed it just to kind of give us an idea of what it is and why there's problems with it. Then the second thing we did was we actually added an ID to each piece of data in the data set, and we used the ID to create a training set and a test set based on the ID. and that ID allowed us to, regardless of whether we like add more data to the data set or we split it into a training set or a test set 100 times, it's still going to be the same training set from the beginning. The data that was in that training set is going to also be in the training set every time you run this code. And the data that was in the test set the first time you ran these functions is also going to remain in the test set every single time. So that's just by adding an ID to each piece of data. And then, so we're just starting to move on to this here, where, let's see, we have that. We left off here. So this one we were adding an index to the data, and here we're adding an ID to the data. So I'll start off just right here, start working our way down, and yeah, the next method is just using a built-in method from the Scikit-Learn called model selection. And this is specifically a train test split. So this is a method built in Scikit-Learn that allows us to create a training set and a test set, and also keep it consistent over time. If as I'm reading through this, you see any words that you don't understand, like even data frame, or there's a lot of statistical knowledge and just like new lingo, feel free to just stop me and say, hey, I don't know what this is. Or if you don't feel like interrupting, which may even be better, feel free to just be like, oh, I don't understand that word. Assume other people might not even understand that word, and just go do a quick Google search and then share it in the chat, or just share with me. Does anyone have any questions before we start working through this? Cool. Welcome back, JH. Welcome back, Antoinette. Nadia, hello. John, hello. Welcome back. Bung, hello. Welcome. Hey. Alright, so I will go ahead, start working through this. We are going to be encountering a lot of code, so as I stop, feel free to just converse among yourselves about whatever we're reading through. So we left off here. Unfortunately, the housing data set does not have an identifier column. The simplest solution is to use the row index as the ID. So we actually had a method here that added an index to our set. Let me just actually run the code one time so everyone can see what we're getting here. So we get the histogram. This is the data set here. Each property in the data set has these features, has 9 features. So longitude, latitude, housing median age, total rooms, total bedrooms, population, households, median income, and median house value. And so I think there's like 60,000 or more properties in the training set. Let's see. There are 20,000 properties.
I think 20,000 is in total.
Yeah, 20,600 in total. And then when we split it into, let me close this out.
What is it?
Yeah, I'm just seeing if I'm actually going to comment these out anyways, because we're going to be moving on to the next method anyway. So yeah, Okay, so if you use the row index as a unique identifier, which we did previously, you need to make sure that the new data gets appended to the end of the data set. So whenever new data is added to the data set, you're just appending it to the end so that they have different indexes, and that no row ever gets deleted. If this is not possible, then you could try to use the most stable features to build a unique identifier. For example, a district's latitude and longitude are guaranteed to be stable for a few million years, so you can combine them into an ID like so. So I'm going to go ahead and type this out. Feel free to type this out or just chat or ask questions. We're going to be commenting this out in a minute anyways, though, I believe.
I think you would need to do that housing with ID is equal to housing dot reset index.
What do you mean?
So the housing with ID basically was created from like you can see that you need to uncomment the line number 56.
Why?
Housing with ID is not you need to create that like in line number 59 housing with ID you need that data frame, right? So line number 56 is creating that housing with ID data frame, and that you need to use for line number 59. You can see line number 59 housing with ID, it's a data frame, so that it's not created up, so that is created at line number 56.
Oh yeah. This is just adding the ID to the housing with ID. Yeah, you're right. True.
We're creating a very long object. What's the data frame? An array or an object, or
It's like a table, right? You wanna?
Yeah, it's like a table. It's like a table object.
Alright, so basically what it seems these two lines of code are doing is we are using the longitude property and the latitude, or I should say attribute, and just multiplying it by 1,000 to create a unique ID, and we're going to add that unique ID to every single one of the 20,000 properties in the data set. And then we're going to use the split data with ID hash, this method we have here, to actually split the entire data set into 80% training data and 20% test data. And the column we're using to split it is the ID column, the value of the ID column. So Scikit-Learn provides a few functions to split data sets into multiple subsets in various ways. The simplest function is train test split, which does pretty much the same thing as the shuffle and split data. So this one that we had up here that we defined earlier, with a couple additional features. First, there is a random state parameter that allows you to set the random generator seed. Second, you can pass it multiple data sets with an identical number of rows, and it will split them on the same indices. This is very useful, for example, if you have a separate data frame for labels. Does anyone want to do a quick Google search and just see what's the benefit of having a random generator seed? And when you find something, just let us know. Train test split. Alright, so I'm going to comment all this stuff out because we're actually using Scikit-Learn to split the data. And we're going to use the original housing. What's up?
It's just a better way to have a variance between your between random sequences.
A variance between random sequences.
Yeah, so you can have like different different random sequences with the random seed.
So by changing the number, you're gonna change which properties or which data in the data set go in training and test, essentially.
Yeah, it gets you closer to true randomness. Like in JavaScript, you use the math.rand function. It uses a random seed, but it uses the same seed every time. So you'll get very similar results. And some stuff will be at the end all the time, some stuff will be at the beginning. So if you regenerate that seed every time, then you get more actual randomness in the result.
Okay.
So is that random function, is that random parameter is basically a seed basically, right? Or just like a random factor to how you randomize the data? Is it the seed value? Like, so when you say that randomize something based on a seed value, so that basically makes sure that your randomness is also like uniform, right? Because again, when you randomize using that seed value, the same data, you basically the results, the final results which you achieve are not that different, right? So is that what this random value is handling? Was that clear? Like,
In the
Yeah, I'm not sure your question. Are you trying to ask like how doing a new seed makes it more random, or how the random function in Python works off of a immersive?
so one thing which I know that whenever you randomize your data based on a seed value, so let's say you use some seed value, it basically randomize your data, and when you like do some analysis on that data, like perform a model, it gives you like certain results, like certain MSC or like certain metric value. But like, so a lot of people what they do is they try to like rerun the randomization, like rerun the model again and again. So like obviously it's random, right? So if you again randomize the data without using any seed value, it might give you like some different results, right? Because you're randomizing usually it is used for sampling basically. The randomization usually is used for like sampling, because like for example, I think during the last call someone mentioned about the sampling, that if you have like a very huge population, you just analyze a sample, and then based on that you incur some results for the population, because you cannot analyze the entire population, you basically analyze a sample. So in order to get that random sampling, you basically use a seed value, so that like it makes sure that your iterative analysis is not too different. So that's why the seed value is usually used. That's what I think. So I'm not sure if this seed value is handling this random parameter is doing that seed value, or it's just making sure that it's randomizing the data in some way. Like,
right, is your question that that random state variable is using the parameter as a seed? Is that
Yeah.
what your question is?
Yeah, that's what I'm like. What that random?
Yeah, I don't know what that random state is. Once it's stated, the random allows you to set the random generator seed. Yeah, I mean that's what it says.
Okay. Then it's good. Like, yeah. So because like it can randomize the data, but like it shouldn't, like I'm not sure when you say randomize, like it should be like randomizing the data in a particular, like it should, like I feel, I'm not sure, like when you randomize data, it might mess up the model if you like just keep on, because you perform an iterative model kind of thing when you like
That makes
random.
sense. Right.
So it's important to understand that a PRNG, a pseudo-random number generator, is absolutely not random in any way. A PRNG is not random. It is pseudo-random.
Yeah,
if you
right.
don't know the seed, the output is indistinguishable from random. But if you do know the seed, it's totally predictable. We want that for unit tests. We want that if Alice runs it and says, oh, this is work out, she hands it to Bob. Like, Bob, could you run this? It would be nice if Bob ran the same stuff.
Yeah, so yeah, random seed generators are basically like an illusion of randomness, because you can infer that.
Yeah, it basically randomizes the data with a factor. So if you don't put that factor, like it's very difficult to predict in an iterative model what will happen.
So I went
For
ahead.
example, if we had
Go ahead.
For example, if we had a random number generator that is doing coin flips, so it produces one bit at a time, and Alice feeds it with 42 and then runs the PRNG, the first couple of values that come out might be head, head, tail, head. She feeds it with 42 again, and she runs it again. It'll produce head, head, tail, head. She runs it a third time, the same thing. She gives it to Bob. If Bob doesn't feed it, then there's no telling what the results will be. But if Bob feeds it with 42, we guarantee he's going to get head, head, tail, head. It's pseudo-random.
Right, that makes sense.
Mhm. So if anyone's having trouble getting Scikit-Learn library to work, the book has it as Sklearn as the library name, which it still allowed me to import it like that, but I had to install the library with this right here. So it's actually spelled out more. Just a heads up. And then I went and I printed the training set and the test set, and so we have our training set here. You can see our training set is about 16,000 rows, so 16,000 properties out of the 20,000 that we had, and the test set is about 4,000 rows, so about 4,000. You can see that the training set is 80%, the test set is 20% of our overall data set. So far, we have considered purely random sampling methods. This is generally fine if your data set is large enough, especially relative to the number of attributes. But if it's not, you run the risk of introducing a significant sampling bias. When employees at a survey company decides to call 1,000 people to ask them a few questions, they don't just pick 1,000 people randomly in a phone book. They try to ensure that these 1,000 people are representative of the whole population with regard to the questions they want to ask. For example, the U.S. population is 51.1% females and 48.9% males, so a well-conducted survey in the U.S. would try to maintain this ratio in the sample. 511 females and 489 males. That makes sense. At least if it seems possible that the answers may vary across genders. This is called stratified sampling. The population is divided into homogeneous subgroups called strata, and the right number of instances are sampled from each stratum to guarantee that the test set is representative of the overall population. And this is a problem that they also have in like a lot of studies that I read too, because a lot of studies that are done in colleges, they're done on the students at the college, or they're done on people in the local community, and it's like, how are you going to use the people of the local community in, like, say, Detroit, Michigan to represent all of America? You can't, and so that's basically a flaw with the study. You really need to have a solid representation of the diversity of America if you actually want to represent all Americans in the study. So this makes a lot of sense. If people running the survey used purely random sampling, there would be about 10.7% chance of sampling a skewed test set with less than 48.5% female or more than 53.5% female participants. Either way, the survey results would likely be quite biased. That's good to know. Suppose you've chatted with some experts who told you that the median income is a very important attribute to predict median housing prices. You may want to ensure that the test set is representative of various categories of incomes in the whole data set. Since the median income is a continuous numerical attribute, you need to create an income category attribute. Let's look at the median income histogram more closely. Back in figure 2.8, most median income values are clustered around 1.5 to 6, so $15,000 to $60,000. But some median incomes go far beyond 6. It's important to have a sufficient number of instances in your data set for each stratum, or else the estimate of a stratum's importance may be biased. This means that you should not have too many strata, and each stratum should be large enough. The following code uses the pd.cut, that's the pandas library function, to create an income category attribute with 5 categories labeled from 1 to 5. Category 1 ranges from 0 to 1.5, so less than 15,000, so basically like 0 to 15,000. Category 2 from 1.5 to 3, so 15,000 to 30,000, and so on. Okay, so instead of actually representing the median salary with dollar values, they're turning into categorical data. Basically, it looks like bins. So I think I already have Panda installed. Feel free to comment on any of this stuff that we just chatted about or that I read right here when it comes to having accurate sampling and stratified sampling, strata, all that stuff. Or if you did any research on any of those words, feel free to share them now.
Was it for the when we this? Is it about like the split function which we use? Is it about that?
Yeah, first we need to define what stratified means. So,
Yeah. One thing which I noticed is I was just trying to play with that random state value. So if I remove that parameter, the standard deviation, the variance of the income keep on changing. But if you set a random state value, the variance of the income doesn't change. Like even if it's random, the values, but the variance is the same. That's something which I noticed. Like if you
Even
remove,
if it's pseudo-random, which means predictable.
yeah. So that's something which I was just trying to notice. Like what? So variance doesn't change if you set a random seed value.
Yeah, I went ahead and so we're talking about we're actually running this stuff on the split that we did with the Scikit-Learn library. So we passed in our original data set, and we used that random state. Now we're actually taking our original data set, the housing data set, and we're going to take the median income category. So it's in here. Actually, I think it's up here is more clear. Yeah, so we have our median income, and
so yeah,
we're gonna place.
The stratified like, random sampling is it's basically just like like a categorical way of dividing your population into groups called stratums, and you can just infer from it.
Kind of like categorical data in that it has low cardinality. You might have a favorite flavor category for ice cream that is vanilla, chocolate, strawberry, and there's no obvious way that you could order those categories. What's different about strata is that you certainly can order them. And sorry, I should observe that you can order them, and we believe that has an effect on y, on the value you're trying to predict.
Yeah, that makes sense.
Hey, sorry, can you repeat it? Like, sorry. Oh, what did you say about the categorical thing?
You can order them, so
Oh,
based
okay.
on the ordering, you can like make some conclusions about your population.
Oh, okay. Ordering based on the category.
Yeah, I think that's what it's aiming.
Yeah, so if we have like income is high, medium, low. You might assign those values 0, 1, 2, and you could perhaps put together a linear model that says the expected home sale price is going to be like double the strat value or some other coefficient stratum value. In contrast, if we've got favorite ice cream flavor, you can't meaningfully say that chocolate is greater than vanilla, and you probably couldn't put together a linear model that would predict the price of an ice cream cone from the 0, 1, 2 values that you assign to those flavors.
I'm just looking into exactly what this. I'm newer to Python, so I want to see what these libraries are actually doing. So for those who are newer to Python as well, the PD cut function in pandas is used to segment and sort data values into bins. So that's basically what we're doing here. It's useful for going from a continuous variable to a categorical variable. So basically what we're doing is we're taking the median income column from the housing data set, we're placing it into one of these bins right here, and we're giving it a couple labels. We're going to take that income category, find out the count, sort, create a plot, bar graph. We're going to make the X label income category, the Y label number of districts, and then we're going to show the graph. So if you go ahead and we run this again, you'll see this is it right here. So you could see for the Y label, number of districts, X label, income category, and then most of the properties are in bin 2 or 3. And so we converted that data into categorical data with this code right here. Pretty cool. All right, so now you're ready to do stratified sampling based on the income category. Scikit-Learn provides a number of splitter classes in the Scikit-Learn model selection package that implement various strategies to split your data set into a training set and a test set. Each splitter has a split method that returns an iterator over different training and test splits of the same data. So this is basically recreating that categorical data. To be precise, the split method yields the training and test indices, not the data itself. Having multiple splits can be useful if you want to better estimate the performance of your model, as you will see when you discuss cross-validation later in this chapter. For example, the following code generates 10 different stratified splits of the same data set. So we're using the same model selection as we did for the train test split. Now we're doing a stratified shuffle split. So it seems like we had this is one method of splitting, and then this is another method of splitting it, right?
I think in this basically creates like, I'm not sure, but it's like, let's say if you have a population of, let's say, 100. So I think it basically creates like, and let's say if you want to split it into like 0.2, so I think it would create those test sizes of like, let's say I'll choose like out of the 100 population, I'll choose first 20 and the rest 80 would be the train. Then I'll choose the next 20 and the rest 80. Like basically I think it's setting different test sets within and the rest is he's setting a train set. So I think using cross validation, he can then basically find the best test set. Like basically try to use like different test sets to observe the evaluation of the model. I think.
What is cross validation? Is that basically comparing
So it basically you use different samples iteratively to find the best sample based on some metric like mean square error or something.
Right.
So that because it's like you basically are giving the model, like let's say you use a certain test set and a train set. Let's call it test 1 and train 1. Now you give the model will give you a certain evaluation. and it will tell, let's say the model evaluation is, let's say it has like 90% accuracy.
Okay.
So now what you do is you basically give, like now you use a different test sample, and the rest will be the train sample. So I think it's like you basically are like, it's like you're giving the model.
Iteratively? Are you iteratively like getting? Are you
Yeah.
sampling after you
Yeah.
get? Okay.
to get the best ratio, basically, or like the best sets, best training, something like that. I mean,
Yeah, that makes sense. Okay. Yeah, that makes sense.
yeah, I'm also actually checking like again just to ensure that what I said is right. But that's what like cross validation is. Basically, you need to perform iteratively to find the best it's like best combination. That's why usually you use cross validation. So
Right. It just at a high level, it just makes the training more accurate. So
yeah.
Does anyone know what this code right here is doing? Exactly, though? This here? Is that what you were just describing?
That's what I'm checking. So basically, it's train test is split. So yeah, it's splitting the data based. I cannot see what that dot split function is doing. Like, can you just
This-
complete dot split?
This one here?
Okay. Yeah. So this dot split function is basically splitting the data. Yeah. So basically, you can see it's creating multiple train and test subsets.
Multiple, yeah, so it's breaking it down into 10 training and test sets, right?
Correct, yeah. So 10 subsets of train and test, where test is 20% and train is 80%. So it's creating basically 10 subsets of train and test.
Yeah, so basically if we look at our previous training set, so our previous training set was 16,000 and our previous test set was 4,000, then that means if we split it up into 10 training sets and 10 test sets, that each training set is going to be 1,651, right? And each test set is going to be 412. So you're basically just creating multiple training and test sets. That's what we're doing, right?
Yeah, that's what I think. So I mean, we just run it and you can see the dimension of the train and the test set in the list. That's what I'll also do.
Yeah, that's what I'm going to do. Because it looks like when we have strat splits, so we have this strat splits array that we're creating, and then this for loop is going to actually split it into 10 different, and then if we target the first one of the 10, then we should get the first one. It should be 1,651 training and 412 tests. So if that's right, then we're right about what this is actually doing. Let me go ahead and just type it out. All right, let's strat train set. Strat test set. There we go. Let's run this. No, it's still 16,000 rows. Let me find out what does it doing. Feel free to do your research too, everybody. And then once this pops up, I'll check it out and I'll keep moving. Overall, stratified, random. Oh, strat splits. Yeah, huh. That's interesting. It's creating an instance of stratified shuffle split, which is a method for splitting a data set into train and test sets in a stratified manner for machine learning. It's typically used for tasks like classification. So n splits, this parameter specifies the number of splits or iterations you want to perform. In your case, you've set it to 10, which means the data set will be split into 10 different train test pairs. Alright, so yeah, we were right. This parameter determines the size of the test set in each split. Test size. Random state 4.2. Huh. Okay.
So the size of every test set and every train set would be the same, 80% and 20% of the total data. But that the distribution that test set the test set would be different in every cases. That's what I'm saying. So size is going to be the same, like what you did above the train test, but basically this is just a list of the train set and test set. So the size should be same in all the list values of the train and the test. That is 80% and 20% of the total data.
Mm-hmm. But if we split it into 10, then it should be, and we're just targeting strat split 0. Huh?
We are not splitting the train and the test. We are splitting the total data into train and test, but so let's say if you split that 100, let's say 20,000 data into 16,000 and 4,000, right?
Mm-hmm.
So that's train and test. Now this would be one subset in that list. Now the next subset again would be 16,000 and 20,000, but the 4,000, but those 4,000 values would be different than the previous set.
Oh, okay.
Just shuffle it.
Okay. But then don't we run into the same issue that we had with our original function that we just did shuffle and split, where eventually all of the data is going to be in the training set and the test set? Like you're mix and matching, right?
So the way it works is you basically when you let's say when you give first set to the first train and test set, when you give it to the model to validate, you basically make the model understand that this was the test set. Then the next time when you give it, that test set might be part of that training set. So there is a way, like it's basically I need to see like why we do this, but it's kind of like a thing where you basically make the model understand like different test sets.
Okay.
Something like that. I need to say like why you do cross validation.
I get what you're saying. I'm just trying to understand why we're doing it like this.
So
Yeah.
why would you do it? Yeah, right.
Yeah. Alright, so since stratified sampling is fairly common, there's a shorter way to get a single split using train test split function with the stratify argument. So we're train test split, passing in our housing data set, 80% training, 20% test, stratified housing. Okay.
Oh, okay. Yeah, I think I understood.
Go ahead.
So basically, the thing which we did for stratified was, so basically it was done based on the median income, right?
Mm-hmm.
So the thing I think it is handling is that in median income, there are different, different distributions of the median income. So when you saw the graph up, like above, basically the distribution of the median income, the ranges which were given, the bins. So I think it's trying to make the module understand for different distribution of median incomes of train and test subsets.
And this is because the median income was priority as far as attributes go.
Yeah, median income is like it's a priority. It's a priority. It's like a significant variable in the data.
Yeah,
So
yeah.
it was trying to like understand the model based on different median incomes, because you can see the median incomes, like the distributions were different, right?
Mm-hmm.
So I think that's what I think. That's why it is like trying to use the stratified so that the model gets more robust. If you give like multiple distributions of train and test subsets for the model to like evaluate.
Mm-hmm. Okay. All right. Good to know. If anyone else wants to add to that, feel free. Just say, I have more to add. I'm gonna just write this out here. Feel free to comment or add anything now, or just code along. I know most people are coding along, so.
I just want to make clear that if Stratify is also making keeping the same percentage if we from each category. If we like selected Stratify by some income category, it will take like the percent of rows from that category proportional to the how big the category is. So that's why it's like 34.
Yeah, it makes sense, right?
Mm-hmm. Cool.
Yeah, because the distribution was way different, like for every income category. So I think it's trying to like go with the relative to the income category when it's distributing the data. That's right, correct?
Yeah, I want to say that if we have one being like 10%, so we will take 10% of our train and test kit from that being. So if you got me.
So the ratio is basically uniform. So
Yeah, that's why it was 35, and that's why I divided it by beans.
right.
Mm-hmm. Cool. Alright, so let's see if this worked as expected. You can start by looking at the income category proportions in the test set. You can see the value counts. I went ahead and I printed that out as well. Divided by length. Let me go ahead and do that. Yep, so we got, alright, and so total they add up to 1, right? With similar code, you can measure the income category proportions in the full data set. Figure 210 compares the income category proportions in the overall data set, in the test set generated with stratified sampling, and in a test set generated using purely random sampling. As you can see, the test set generated using stratified sampling has income category proportions almost identical to those in the full data set, whereas the test set generated using purely random sampling is skewed. Okay, so overall stratified, random, stratified error percentage, and random error percentage. Okay, so basically, the error percentage when you use the random method opposed to the stratified method, the errors are going to be much higher. So you're going to get you're going to get your stratified bins are going to end up being more accurate and more closely representative of the overall data set than if you randomize it. Does that sound right?
Fair enough.
Mm-hmm. Okay, cool. So you won't use the income category again, so you might as well drop it, reverting the data back to its original state. Set drop. I'll just copy and paste this to make it quick. Alright, so we spent quite a bit of time on test set generation for a good reason. This is an often neglected but critical part of a machine learning project. Moreover, and I'm sure we're only skimming the surface, moreover, many of these ideas will be useful later when we discuss cross-validation. Now it's time to move on to the next stage, exploring the data. Explore and visualize the data to gain insights. So far, you have only taken a quick glance at the data to get a general understanding of the kind of data you are manipulating. Now the goal is to go into a little more depth. First, make sure you have put the test set aside and you are only exploring the training set. Also, if the training set is very large, you may want to sample an exploration set to make manipulations easy and fast during the exploration phase. In this case, the training set is quite small, so you can just work directly on the full set. Since you're going to experiment with various transformations of the full training set, you should make a copy of the original so you can revert back to it afterwards. So I'll go ahead and okay. Cool. Visualizing graphical data. I wonder what state this is. Because the data set includes geographical information, latitude and longitude, it is a good idea to create a scatter plot of all the districts to visualize the data. So let's go ahead. Kind, scatter. We got this graph here. There we go. Each one of these dots is a different district. And then we have the latitude and the longitude. Cool. This looks like California, alright. But other than that, it's hard to see any particular pattern. Setting the alpha option to 0.2 makes it much easier to visualize the places where there is a high density of data points. Alpha 0.2.
Is it because to check like certain areas are kind of like would be kind of like of high income or like high property prices, and it's like kind of to identify any outliers or something in the data? That's the reason we're doing it.
The reason we're doing what?
This scatter plot and like to find out like the which areas like have more density, or like find out any outliers, as in like density in some other population, other location. For example, California, like I mean San Francisco is more costly, but the income rate is also, the median income is also a bit high there. But the same goes for like some other location which is close to San Francisco, but it would be like less prices for like property. So that would like have some skewed data, right? That would like, because like I mean it would kind of like have like more variance between the data or something. Is that might like affect the model. Is that why we are doing this?
As far as I know, we're just doing this to actually visualize the data, but does anyone else have any input on that?
Yeah, so we're
You're not gonna get any outliers. You have to use some like a box plot to see the outliers.
Sorry, I said the wrong term. Outliers as in like I was thinking from the perspective like or like locations, like for example San Francisco, if like say entire population is close to San Francisco, then like we could say that it's kind of analyzing just one district or one location for like the model to understand the prediction of the price.
right. So this basically gives us a better way for our model to look at that specific density. So I think that's what we're leading into.
I mean, what if like there are some, let's say this scatter plot would have been in such a way that the points, some of the smaller like let's say some smaller density was kind of like a bit away from that close density, or let's say like there were like more clusters formed in that. So would that would have affected the model, right, or something?
Yeah.
Yeah, I was thinking from that perspective.
But I think we're just visualizing the data right now.
So a question on the table is, why would we do this? And a very common motivation would be data quality analysis. Figure out if someone tells us, oh, I'm giving you Nevada and California real estate observations, and we eyeball this visualization, and we can tell at once it's lying. We don't see Reno, we don't see Las Vegas appearing in this data set at all.
Yeah, it's like the shape of Texas or something. We're like,
what we're looking at here is where the people are. You can compare it with what satellite sees in the evening. Where is the artificial illumination in the state of California? Same thing here. We're not looking at anything beyond lat long. We're not examining median income. We're not examining the home sale price. It's just where do the people live.
Yeah, I would agree.
true, because the only data that really proves that this is California is latitude and longitude. There's no like city names or state names in the data we were given. It's basically just other categories, and latitude, longitude allow us to visualize it in a way that does confirm that it's California. That makes sense.
Yeah, we're just looking at the population. But yeah.
Yeah, I mean the reason I brought about that median income thing is basically, so within California, I just want to ask you this, like you guys have stayed in America a lot. So, like I want to just ask you, like, are there like ranges in prices within California as well? Like, or like difference in the income, like large difference in the income within California, like large difference in the property prices within California as well?
Of course.
Would that happen?
Yeah, sure.
Yes, I would agree.
So that's the reason I was asking, like, let's say like for now the data which we saw, like it wasn't like having a very large difference in the distribution, like in the median income, or like, but if something like that happened, then like this, because they haven't given like a certain data belongs to San Francisco, the only thing which they have given is like latitude and longitude. So only through that, by using this scatter plot, we can understand. So there is a difference in the median income in the data. Why is that? So that could be this reason. Like we can use this scatter plot to understand, right? That okay, this certain area has a large density. So if we just capture this data, then we can understand that the median values are very different in this area. That's the reason the median values are different. Or like the incomes are different, or prices are different. That's the reason I brought that point.
Yeah, I think.
That sounds valid.
Yeah. I think we're going to add more dimensions to the actual visualization that does give us that information as far as the median prices go too. So I believe that they add that later on. All right. So next you look at the housing prices. The radius of each circle represents the district's population. Option S, and the color represents the price. Yeah. So basically, you were saying, adding the price. Here you use a predefined color map option C map called Jet, which ranges from blue, so low values, to red, high priced values. So I'm gonna go ahead and type that out. Feel free to comment or just chip in or just code along. I'm sure most people are just coding along. So S, we're using population. Test this out. I should comment out some of this other code so the diagrams don't pop up every time, but all right. So yeah, this is way more clear. So the size of the circles are telling you the population, and the color of the circles are telling you the price, the average price of the home, I believe, right? Median house value, yeah. So we have population represented with S, so the size of the circles, and then the median house value represented by C, the color of the circles. Interesting. Okay, cool. This gives way more information. And you were right, Aditya, that, you know, the more densely populated places seem to be the more expensive places for the most part, but not entirely. You do have a couple outliers here too.
Yeah, I mean, one thing which I can understand, I'm not sure if that would be like a good thing, but so the low population, like the mid population and like the high population is usually like going along the southwest coast. Like it's not a coast, but like it's kind of like the southwest border,
Mm-hmm.
and the upper border, like the upper area is kind of like less population. So the data which we have for like the mid and the high population is less. So if the model trains, I'm not sure. So based on the location, then it might like, I'm not sure, but it might not give like a better result based on the location. That's what I think. Like if we like just consider, like for example, like someone, let's a model is done and someone wants to predict that this area, like would I be able to get a better predict the price for this area, then that might, if that ranges within that bottom border, that might be like that might not give like the correct value, might not.
Mm-hmm. Does anyone have any thoughts on that?
So one way to interpret this is the rich get richer, the big cities get bigger, and early in California's history, water transport was coastal cities were a big thing. The other major waterway that you see here is the green splotch in the middle is Sacramento, the state capital. And you can go from the San Francisco Bay Area up the American River to Sacramento, and you'll see that because of waterway commerce, there was also a bunch of people that moved there, and then, as I said, big cities get bigger, and that drives up the cost of each dwelling.
Yeah, that makes sense. So this image tells you that the housing prices are very much related to the location, close to the ocean, and to the population density. As you probably knew already, a clustering algorithm should be useful for detecting the main cluster and for adding new features that measure the proximity to the cluster centers. The ocean proximity attribute may be useful as well, although in Northern California, the housing prices in coastal districts are not too high. So it's not a simple rule. This is what we're getting here. So next we're going to look for correlations. So since the data set is not too large, you can easily compute the standard correlation coefficient, also called Pearson's R. And I'm going to go ahead and just, I want to dig into any of the statistical terms. I like to look up later and just, do a few searches on them. But if anyone has any information on the standard correlation coefficient or wants to break it down in simpler terms for everybody right now, feel free to do that. Since the data set is not too large, you could easily compute the standard correlation coefficient between every pair of attributes using the core method. I believe this is just telling us how important each attribute is. How important each attribute is to determine the actual price. So you can see like population, longitude, latitude, they're not giving us too much information regarding the price of the house. Obviously the median house value is giving us more information. That's how I'm interpreting it. Go ahead.
So correlation is exactly show us if median house value is growing up. So how much growing up? Another, for example, median income. If they have minus before the number, that means when median house value grows up, so population rate goes a little bit down. Mean correlation.
As the house value goes up, the population goes down.
You see, population is minus 0.02. Because of minus, it's like not growing. It's going down.
It's shrinking. So you're telling me that longitude and latitude go down as the house value goes up too?
Looks like that, but you see, if correlation equals to 0, it doesn't correlate, doesn't react on the growing of the median house value. So if it's closer to 1, that means correlation is big. If it's closer to 0, that means it doesn't change with changing of median house value.
So you can think of like correlation as like a significant mean that correlates to some problem.
Yeah, it depends on what which value we select. It's like if it's median house value, it is equal to 1 because it's like the same.
Yeah, that makes sense. All right, so as the median house value increases, the income of the people living in the area increases. That makes a lot of sense. Like that seems pretty obvious. Okay, cool. Yeah, so the income seems to be the most important attribute to determine the house value, right?
Yes, it has the most correlation.
So now is the model gonna is the model gonna like weight median income higher than any of the other attributes based on this, or is it gonna do it with other strategies? Just curious. I know we're gonna get to it, but that's what it seems like.
thing is all this is getting correlated with the median house value. I'm not sure if like is there any way to also like check if how the median income is, or because I mean let's say if other variables, like you can say that the other variables on this in this we are only checking the median house value. Okay. So basically I was just saying that the other variables might be correlated with each other as well. So if they are strongly correlated, if like one variable considered like will also be affected by the other variables which are correlated with the median income, right?
Yes, we can also create heat map which will show correlation between all of our
Other variables.
yes.
Okay. Cool. So the correlation coefficients range from -1 to 1. When it's close to 1, it means that there's a strong positive correlation. For example, the median house value tends to go up when the median income goes up. Okay. When the coefficient is close to -1, it means that there is a strong negative correlation. You could see a small negative correlation between the latitude and the median house value. Prices have a slight tendency to go down when you go north. That kind of makes sense because it gets colder and no one wants to live in cold temperatures. Finally, coefficients close to 0 mean that there is no linear correlation. Alright, cool. So, yeah. Okay, this all makes sense. Another way to check for correlation between attributes is to use the pandas scatter matrix function, which plots every numerical attribute against every other numerical attribute. Since there are now 11 numerical attributes, you would get 11.2 equals 121 plots, which would not fit on a page. So you decide to focus on a few promising attributes that seem most correlated with the median housing value. So let's go ahead and add this here. Okay, see what we're doing.
Yeah, there doesn't seem to be any relation between the other variables. It seems like it's median income and median house value and median house value and median income. Yeah, total rooms and I think median age basically is kind of negatively correlated slightly, right? Positively correlated. Slightly.
So we use so we basically use this right here, the correlation matrix, to decide which attributes we want to dive deeper into. Like anything that's over 1, it might not be important, it might not be related, or the correlation might be random or not connected in any way, but this is telling us like, hey, dig deeper, explore further, find out for sure whether it's really correlated or not, right?
Yeah, because also relationship can be non-linear and correlation shows like this shows us linear dependency.
Mm-hmm.
Not dependency, correlation.
Mm. Yeah.
Yeah, it's like linear regression.
Yeah. Okay, so looking at this right here, you could see the correlation in this here or what?
I could see median income on the left and total rooms down. You see, it's a bit like side-shift right. Median income on y-axis and total rooms on x.
Yeah, second row and third column.
Yes,
Second row, third column right here.
this one.
Uh-huh.
You see, it's like
Yeah, so as the total rooms go up, the median income goes up.
Yeah, so we could create linear regression where we could put the straight line.
Mm-hmm. Mm-hmm.
Right.
Same with this one
Linear
here.
regression is basically like a best
Yeah.
fit, a best fit
Yes.
line. Okay.
Yes, this is the
Mm-hmm. All right.
also median house value and median income. You see, it's a little bit different angle.
Mm-hmm.
In extra in second column, you will see like something.
Yep.
The slope is less
Yeah.
with median income to median house value.
Yes. It's just different axes.
But it's still linear, so I think linear regression should work on this.
Yeah.
Mm-hmm.
What do we think the units on total rooms is?
The units?
Yeah, those seem crazy large numbers.
Total room.
Has this been scaled, perhaps?
Let's make sure it's matching here. Yeah, because there's no way it's like a 10,000 room property. My guess would be it's scaled, multiplied by 10,000. So like maybe 1 room, 2 rooms, 3 rooms, 4 rooms, or nah, it's got to be more than that though. Because you're telling me the house with the most rooms is 4 rooms? Nah, there's no way. It's got to be more than that. Yeah, I'm not sure exactly.
Yeah, I'm just worried that possibly we're confusing rooms with square feet.
Possibly.
Huh.
It's a landmine that Giron deliberately planted for the reader to uncover.
Perhaps.
Yeah, I wonder if we'll get into it later in the chapter too. Yeah, that's a curious thing there. All right. So I'm gonna finish reading. Actually, I mean, we'll end right here because it's 7:29 right now. So we have a minute. We could kind of just unplug a little bit, kind of debrief, and then we will start here next week. So this is a good spot to stop. And then we start digging into the actual linear correlations more. So yeah, what does everyone think so far?
This was great. Thank you for taking the time to read through this and showing us how this works.
Yeah, thanks for showing up and contributing, for sure.
Thank you.
Thank you.
Cheers all.
Yeah, I will. I'll see everybody next week at 6 p.m. Eastern Standard Time.
So thank you, Tom.
Yeah, thank you.